Thanks for the nice introduction, and thank you for having me here. It's a pleasure to be here and giving this talk, and thank you everybody for coming. Can you hear me well? Yep. Oh. So, as I said, today I'm going to be talking about some of my research on establishing secure and privacy-preserving blockchain applications using real-world cryptography. And before that, I wanted to give a bit more broad overview what I'm interested in. So I'm interested in general on information systems that we are using today, so systems that we can actually use every day. And in order to achieve security in those systems, we need to employ cryptography. And there are many tools for that that have been developed over the many years, like fully homomorphic encryption or zero-knowledge proofs or multi-party computation. The challenge comes when we want to use these theoretical constructions and use it in practice, because there we have many restrictions. We are restricted by the systems because they give us restricted computation, or the amount of information that we can store is also reduced. The battery that we have, for example, in our phone is actually restricted, or the cost of executing a certain cryptographic tool, for example, in the blockchain, takes a lot of cost in terms of even monetary fees. So in general, I will say I'm an applied cryptographer, which has a high interest in general in security and privacy of these information systems. And I will say I'm working in the intersection of the two, information systems and cryptography. And in general, I like to design and analyze cryptographic protocols that, on the one hand, are practical for the restrictions of current systems that we have today, but on the other hand, provide meaningful security and privacy guarantees. Okay. But as Clara said, the main focus in the last years have been in blockchain. So of course, we are going to talk about blockchain. So what we need to know today about blockchain is really simple. So basically for us today, a blockchain is an immutable append-only data structure that we are going to call the ledger. And this data structure is maintained by a set of participants that are distributed worldwide and are called the miners, or system are called builders, but basically a set of parties that are geographically decentralized, geographically distributed around the world. And these parties use a distributed protocol to reach consensus about which transactions are valid and can be added to the ledger itself. Okay? So a bit more concrete. So we have several users. So the users in the system are represented by a pair of secret and public key, or secret and verification key. And when they want to interact with the blockchain, what they do first is they create a transaction. A transaction is basically a data structure, doesn't matter much how it looks like, but encodes the fact that certain asset is transferred from one user, identified by the verification key of Alice, to another user, identified in this case with the public key of Bob. This transaction is authorized by the sender. So the sender, in this case, Alice, used her secret key to sign the transaction. And that pair of transaction and signature is sent to the miners. Now the miners run this consensus protocol to decide whether it's valid or not. And if it's valid and they agree on that, then it's added to the ledger, right? So even though we have many blockchains and they have different designs, all of them are based on the same principles. All of them have a concrete shared principle, which is that they want to maintain this shared and public ledger with all the transactions that happened from the beginning. And believe me, in Bitcoin, for example, we really have all the transactions that happened since Satoshi Nakamoto started it in 2009. Right? So have it. And this is actually good for security. Why? Because now, for the first time, we have a cryptographic currency system that we don't have to rely on a single party, but we can, in a distributed manner, check the verifiability of the transactions, check who owns what, or we can check the balances of the users. However, from the privacy point of view, it's actually not so nice. So having this public ledger with all the past transactions really reveals a lot of information. Okay? And you don't have to believe me, so we can check some of these public ledgers. So we can go, for example, to Bitcoin, and this will be how a transaction looks like. Of course, there are many fields, so don't get scared. But basically, the idea is that we can actually, in this public ledger, see when the transaction happened. We can see how many coins were changed and what's the value, who sends money to whom, and many other information as well. And this is not only a problem with Bitcoin, it's basically with most of the blockchains that we have today. In Ethereum, it's the same. So this is an example of a simple transaction. And again, we can see when it happened. We can see how much money was transferred, which data has been used in this transaction, which other interactions happen in the system. So we can really have a lot of publicly available information. So I want to argue that privacy in blockchains is important. Actually, it's a crucial feature, and this is why I'm interested in researching into it. For example, if from the user's point of view, we want to maintain our transactions hidden, right? So we don't want to reveal our medical bills or what is the salary or what we pay for. Companies also want to maintain their business secrets. So of course, they don't want to reveal from whom they are getting paid or what amount of business they have from the competitors. And the currencies also is important that they have a properties called fungibility, where every coin looks the same as other. They are not tainted. So you cannot see where the coin comes from. So you cannot trace it back. Otherwise, you have a history, and then this deviates the value of the currency itself. So in general, what we have and the problem that we have is that there is a trade-off. There's a challenge between privacy and security. So on the one hand, we want to maintain transactions and balance hidden from the observer. But on the other side, we want security. We want transactions to be publicly available. So how do we achieve the best of the two worlds? How we do that? So to see a concrete example, let me give you a really simple application example. So imagine that Alice wants to buy a book from a bookstore, or from Bob in this case, and she wants to do that by paying in cryptocurrencies, in Bitcoin. What she will do is she creates a transaction, send it, a transaction that pays to Bob, send it to the blockchain. And when this happens, then Alice gets the book from Bob. And intuitively, and we will see later a bit more formally, but intuitively, what we want in one hand is security, right? Or it's also called atomicity. So we want that from the point of view of Alice, like, look, if I really pay to you, better be the case that I get my book back. From Bob is okay, but if I send you the book, I really want to get my money. So we have, it's called for exchange. So we want to exchange two items of interest. In one case, the money, the other, the book. We want that the exchange happen atomically. So both of them happen or none of them happen. From the privacy point of view, we want to conceal who pays to whom, right? So Bob may not want to know how much is charging for the books or how many books he's selling for in 1 month. And a third property that I'm interested in, we call it interoperability. And the idea is that every protocol or the protocols that we develop should be compatible with all existing cryptocurrencies. So we want to deploy protocols that are agnostic of the details of the cryptocurrency below and work for it. So if we look at the landscape that we have today in blockchain with looking through the lens of these three properties, what we have is from the one hand, we have a certain line of work, both from industry like Monero and Zcash, also from academia, Qiskis, and many other papers that are focused on achieving or trying to achieve different notions of privacy. Right? They are trying to hide the amount in the transaction or who pays to whom or certain different notions of privacy. Please note that I'm not saying that it's a solved problem. It's just they are giving different notions and they have their trade-offs, but at least the target of these designs is to achieve certain notions of privacy. However, they don't focus on atomicity, so they actually consider one transaction at a time. So we cannot really reason about how the different transactions are linked to each other. And these currencies work in isolation. So each of them have their own design of transactions, their own properties, so they are not interoperable. We cannot design protocols that work among them. On the other hand, we have other cryptocurrencies like Ethereum, have smart contracts. Smart contracts, basically, the idea is that you have a piece of code where you encode the whole logic of your transaction or the whole logic of your operation. So in that sense, it aims to have atomicity. It means that once you call the smart contract, the whole logic is going to be executed at one go. However, this goes against the notion of privacy because, again, as we have seen, for example, with Ethereum, you can see the whole logic. You can see who calls this smart contract. You can see everything that is being executed. And again, they work only for one cryptocurrency, for example, for Ethereum, but the solution is not universal. It's not standard for all the cryptocurrencies that we have. In academia, we have also some works that are trying to overcome the problem of privacy in Ethereum or in the Ethereum-based cryptocurrencies. Some examples from academia are CK, C star, or the fully homomorphic EVMs. So again, they achieve the atomicity similar to Ethereum. They enhance the Ethereum-based cryptocurrencies with privacy, but still they are isolated solutions. So solutions that only work for one cryptocurrency. therefore they don't achieve interoperability. So the question is, what can we do? So can we have some way to tackle the three problems at the same time? And the answer is that I don't know. And I know it's a bit disappointed. Right? Why I'm saying this is like in this talk, I'm not planning to give you what is the only solution, right? But I think my answer should be more like, I don't know yet. So what I want to show next is a possible research direction that I'm interested in, and I think can tackle the three properties that we have seen: security, privacy, and interoperability. Okay, let's see how it does. So we call it cryptographic application. And the basic idea is that now we are going to create a cryptographic protocol between the parties that is used to generate the transactions and the authorization of the transactions and decide the order in which these transactions are they are sent to the blockchain. Okay? So let me give you a more concrete example. Let's see the example that we have seen before of buying a book. This application is called Zero Knowledge Contingent Payment, and a recent work of us is appearing in ACNS. And the basic idea is that, okay, as before, Bob has the book, and now Bob will create a fresh key, like a password. Then Bob will do the hash over the key and compute the hash value H. And apart from that, he will prove that, look, Alice, there is a key that I don't tell you which one it is, but there is a key such that the value H is the computation of the hash over that key. And I'm encrypting with that key the book that you want. Okay? So this encryption encrypts the book that you want under a key that I don't tell you. And this hash value is the hash of a key that is hidden, and this is the value H. And Bob sends this to Alice, right? Alice, looking at this proof, she's convinced that she doesn't know the key yet, but as long as she knows it, she will be able to decrypt and get the book that she wants. So she's happy with that. And she knows that this key is the pre-image of the hash function. So as soon as the key is defined in this way. Okay, so then what Alice does is say, look, I'm going to create a transaction, Bob, where I give you the coins. But in order to get the coins, you not only have to be a receiver, but you also have to reveal me this key that you mentioned, such that is the hash of the value that you gave it to me. Right? So it's the key that you promised to me. So you have to give me a key, such that if I do the hash of the key, give me this public value. Why that? Because as soon as Bob reveals this thing, Alice can decrypt and get the book that she wants. So when she's happy, she sends this transaction to the blockchain. Now when Bob sees it, remember that the ledger is public, so Bob can see all these transactions, or can see also this one. Then Bob creates a second transaction that says, look, okay, I want to unconditionally get the coins from this condition to myself. Authorize this transaction, add the value, the key that he needs to reveal in order to fulfill this condition, and put it in the blockchain. And because this blockchain is public, Alice can see this, get the key, and decrypt, and get the book that she wants. So it's a lot of detail, but basically the idea is that through a cryptographic protocol that only happened between Alice and Bob, they have coordinated which transactions and in which format need to be created and in which order they are added to the blockchain. So cryptographically, we have done this protocol that does the coordination of transactions between the two parties. This idea of cryptographic applications. This is an example only between two parties, but as you can imagine, it's more complex in the wild. So we have many cryptocurrencies apart from Bitcoin, have CASA, Ethereum, Monero, and many other. For example, an application that uses more than one blockchain at a time is atomic swaps, where Alice wants to pay Bitcoins to Bob, only if Bob gives in exchange some Ether back to Alice. So there are protocols in which you are interacting at the same time with more than one blockchain. And there are protocols where, of course, there are more than two parties interacting between each other. And one example of that is what we call multi-hop payments, where Alice wants to pay to Bob, only if Bob forwards the corresponding amount in Ether to Carl. So basically, we have protocols where we need more than one blockchain at a time, and even that we need even more than two parties at the same time. So creating that cryptographic protocols has been the focus of my research, but doing that is actually challenging. It's not easy. So imagine that even in this simplified version or this simplified view of the blockchain that I'm talking about, where we have only transactions, the authorization of these transactions, and really simple transaction format, we still have many things that we need to consider. For example, this part here is called the code, it's called the logic associated to a transaction. When we look what is supported in the different blockchains, we have really different possibilities. For example, in Bitcoin, we can add code like this, where you need to reveal the preimage of a hash function, as we have seen before, the time lock only. So you can lock the validity after a certain time. In Ethereum, as I said, you can put more general logic. So you can put a piece of code that is more generic at the cost of that you are limited by the amount of gas, the amount of fees that you are paying for that. So the more logic you put, the more transaction fee you have to put. And there are other cryptocurrencies like Monero and Zcash that doesn't allow you to put any code at all. It doesn't allow you to put any logic other than the transfer of a coin from one key to another key. When we look at how transactions are authorized, in the wild is also a mess again. So Bitcoin supports ECDC and Schnorr, which are two different digital signatures. And Ethereum supports ECDC only. Monero supports a totally different digital signature, which is linkable ring signatures. In Zcash, transactions are authorized even not with digital signature, but a totally different cryptographic scheme that is called zero-knowledge proofs. So when we want to generate or design these generic cryptographic protocols, we are in a landscape where we have really limited expressibility of functionality, and it's expensive, like in Ethereum. And really, we not have a common ground for interoperability. So every blockchain have a different digital signal, a different authorization scheme. And this has been appears also in the current state of the art in this area. For example, if we look at another application that doesn't matter how it works, it's called proof of reserves. But the idea of what is happening today, most of the works, is that there is a work for each of the settings that we have seen before. For every cryptocurrency, they really develop a different protocol and a different security proof. For example, for the proof of reserves, we have a paper provisions that give a solution for proof of reserves in Bitcoin. Then we had another one that did the same protocol for Monero, did a design and a security analysis. They found a problem with privacy, so they did yet another design for, they call it Improve Plus. Then they did another one for another cryptocurrency that was called Wimbo, yet another one for another cryptocurrency that was called Numatus. And at some point, I just got tired of looking at these papers, but basically, we are really having many repetitions of protocols for the same use case, for the same application. So to wrap up this part, what I'm trying to do is more a modular approach. So I'm considering a really simple model of the blockchain where the blockchain only understands really simple transactions, really only transfer of assets, of coins between two accounts. The transactions are authorized with a digital signature, only with one cryptographic scheme. And the transaction is valid if this authorization verifies with respect to the public key of the sender. So this is the only thing I'm assuming from the blockchain. And the interesting part is this is a subset of what we have today in Bitcoin, Monero, Ethereum, and so on. And what I'm trying to develop first is what I call generic cryptographic building blocks. And generic here means that the only thing I can use the blockchain for is to submit transactions with the authorization supported by the blockchain below, by a digital signature. Now, using these cryptographic building blocks, I'm generating generic cryptographic protocols for blockchain applications. In general, like cryptographic protocols that only uses this building block to generate the interactions with the blockchain. Therefore, we no longer need a concrete protocol for every blockchain, but only one for this generic blockchain that now can be instantiated in each of the blockchains that we have today. So next, I'm going to give you a concrete example of what I mean with this. So I'm going to give you an example of what I mean by cryptographic building block, and later how we use it to build atomic software cryptographic protocol. Okay, so one example of this cryptographic building block is called adaptor signatures that we formalized it in Asia Crypt 2021. And the basic idea is that we are combining standard digital signatures, the authorization scheme in the generic blockchain that I mentioned, and hard relations. So As you may know, a digital signature is a scheme that has three operations. So we can generate keys. We can generate the secret key and the verification key. With the secret key or the signing key, we can sign transactions, and this gives us a signature. And we can verify with the verification key that the signature created is correct with respect to the transaction. And the second building block are relations. So these are pairs of public values or public statements and private values or witnesses, right? Such that they are in a relation. For example, as we have seen before, the hash of a witness gives you the hash value of the X. Right? And for those of you that knows, the public keys in Bitcoin, for example, are in an elliptic curve, in a D-log group, where the G is the generator of the group. Basically, it's a relation again between the witness, that will be the secret key, and the public element, that is the verification key. Doesn't matter much. The important idea here is that the security property of this building block is that given a certain pair of public statement or a witness that belongs to the relation, concretely, for example, given a key and the hash value of the key, if we give the public value with the hash value, for example, to the adversary should not be able to come up with the private, corresponding private value. Should not be able to come up, for example, with the pre-image of the hash value. So then the idea of adaptor signatures, why we are combining these two building blocks, is that because we no longer have code that we can add to the logic of the transaction, we want to mimic the functionality of this code cryptographically, right? And now I'm going to give you an example of what I mean exactly by that. So we do that again in a generic blockchain. So it means that the only thing that we have is transactions, super simple transactions that go from KA to KB. And from the underlying building block, we can use the key generation, and we can use the way that miners will verify transactions, the verify algorithm. But of course, we can change how things are signed. So this is what we are going to do now after signature. We are change the way that transactions are signed, such that at the end, what we get is a signature that verifies with the corresponding verification algorithm. That is what the miners are actually using. Let me be a bit more concrete. So first, we are changing the signing by an algorithm that we call pre-signing. So instead of signing directly the transaction, we are sending the transaction with the signing key and a public element. What we have seen the example before is the hash value, for example. And this pre-signature object, we can pre-verify. We can verify that it's correct. We can verify that this pre-signature was created by the owner of the verification key, and with corresponding to the hash value with the public element in the pre-signature. Then later, if we learn the private value of the relation, then we can adapt the pre-signature object into a valid signature. And this signature will verify with the verify algorithm of the blockchain, of the digital signature. And finally, if one gets to know the pre-signature and the signature, then one can extract the witness that corresponds to the public value, the witness of the relation between witness and this public statement here. Okay. We have defined the security properties of this scheme as well. So we have one eligibility that basically is similar to signatures. The adversary, without access to the signing key of the honest user, cannot create correct pre-signatures, cannot pre-sign on behalf of the user. If I get a valid pre-signature that verifies with pre-verify, and I get the corresponding witness, then I should be able to adapt. Means I get a signature that verifies correctly. And the final property is called extractability, meaning that if I get a pre-signature that pre-verifies, that is correct corresponding to an X, and I run the extract algorithm, I should get a W, a witness, that is correct, meaning that the witness and the public statement are in the relation. Okay? So these are the three properties of adapter signatures. And maybe it helps if we can see it in a concrete example, how we can use that now in a protocol between two parties to really mimic this code, to mimic this functionality here. Okay? So imagine again the sender and the receiver. Now there is as we said before, there's a public statement that is the hash of some witness, right? So now the sender can pre-sign, can create a pre-signature over the transaction with the public statement and give the pre-signature to Bob. Okay? Now, the Bob first can, so Bob can pre-verify that this is correct by using the pre-verify algorithm. And later in the application, and we will see how, when he learns the witness, he can adapt the pre-signature into a valid signature. And this is what Bob can put in the transaction. Because remember, the signature that you get verifies with the verify algorithm that is run by the miners, by the blockchain itself. And once this is in the blockchain, in the ledger, because it's public, Alice can read the signature. She knew the pre-signature before. So now she can run the extract and she can get the witness itself. So in a sense, by cryptographically, mimic the functionality that if Bob gets the coins, so if Bob publishes this transaction in the ledger, Alice can learn the witness, can learn this value here. But this logic is not done by the blockchain, but is done cryptographically outside of the blockchain itself. Okay, so this is one example of auto signature. So now we are gonna, apart from our work, this has been picked up afterwards. There are new definitions of auto signatures, for example, how to do it for two parties. There are also stronger definitions than the one that I have shown to you. There is also some people that are looking at generic constructions, how you can generically construct auto signatures from identification schemes, and also what impossibility results what are the constructions that we cannot do. For example, it has been shown that we cannot build auto signatures if the underlying signature is deterministic. Okay? There is also different constructions. In our paper, we give one construction when the underlying data signature is ECDSA or Schnorr. We also give one for linkable ring signatures, which is interesting when the underlying blockchain is Monero, example. And we also give some constructions that are secure against post-quantum adversaries. And the other part that has been picked up about this work is that there are many blockchain applications that are using this cryptographic building block after signatures as their building block for designing the application. And of course, we also did it ourselves. So one application that we did is atomic swaps. And the simple idea is as follows. So, as I said before, the application of atomic swap is that Alice has some coins in Bitcoin, Bob has some coins in Ethereum, and they want to swap it. They want to exchange it. They want to do it atomically. So Alice gives coins to Bob only if Bob gives coins to Ethereum. And this is the simplified way where this protocol works is as follows. So they will create what is called a joint account. There is a way to take the keys of both users and aggregate it, such that this is an account that belongs to both, meaning that only when both authorize, they can actually transfer from this key, transfer from this account. And now, first thing that Alice will do is lock her coins in this joint account. So create a transactions that spend for herself to the joint account, sign this transaction, and submit it to the blockchain, to Bitcoin. And Bob will do the corresponding thing, but in the Ethereum side. So he will create a transaction that locks his coins, signs the transaction that locks his coins into the joint account, and submit it in Ethereum. So basically, graphically, the only thing that we have done so far is that they have created this joint account, and both of them have to agree, and lock the coins there. So now we need to somehow find a protocol that extract these coins, but in the reverse order. So atomically, they get from the joint account, the coins back to the Ethereum back to Alice and the Bitcoin back to Bob. But these have to be atomically. So either both of them happen or none of them happen. Cryptographically, what we want to do is that we want two transactions that exchange the coins, as I said, and we want a protocol where they pre-sign, the two parties, they sign the transaction that gives the coins to Bob, the coins in Bitcoin, and they sign the transaction in which they exchange the coin in Ether. So the coins of Ether goes to Alice, and the coins of Bob goes to Bob. The question is, in which order do we do that, right? So if we first sign the first transaction, Bob will get the coins and will just run away and don't participate in the second signature. And the other way around. If we do the first one, how Alice will get the coins and then Bob will just run away. So how do we do this atomically? And this is the focus of this work. Of course, as I said, we are going to use adaptor signatures for that. And this is basically the simplified way of how we do it. So first, Alice will create a pair in this relation I mentioned before. You can think of it as this is a random value, and this is the hash of this random value, for example. Then sends the public value to Bob. And now Bob gets the pre-signature. Remember, it's not a valid signature yet. It's the pre-signature of the transaction that gives him the coins with respect to this public value. Okay. And by the unforgeability property, so meaning that the Bob cannot get a valid signature if he doesn't know the witness, Alice is sure that he will not able to steal the coins yet. So he can get this coin back here unless he get the witness from the public statement, but from the forgeability of the adapter signature, he cannot do that by the security of that. So now they do the same, but for the coins that are in the Ethereum side. So Bob also gets the pre-signature of the transaction that sends the coins to Alice and send it back to Alice. Now, by the adaptability property, meaning that every time that you have a valid pre-signature, if you adapt it with the corresponding witness, she knows it because she got it before, she can get the signature on this transaction. So it means that she can actually submit it to the blockchain and get the Ether. But now, this is the trick, or this is how we leverage after signature. If Bob gets the pre-signature that he got before and the corresponding signature, because they both are valid, he can run the extract algorithm. And with that, he can extract the witness that Alice created at the beginning. Okay? So, and this is due to the extractability property of after signatures. And with that, he can now adapt his pre-signature, adapt it into a valid signature, and submit it to the blockchain. So as you can see here, basically the only interactions that Alice and Bob do with the blockchain is submitting a signature to the blockchain. The rest of operations, pre-signatures, adapt, and extract, are happening cryptographically between the two parties. So this is the goal of this paper. And the idea in general for this cryptographic application is that designing these protocols is hard, or at least require expertise both in how these systems actually work and how you can leverage them. And also you need to learn to know about cryptography. However, once you design them, it has several advantages over what we have, what is the state of the art. So the computation overhead is really low. So these operations that I see here, pre-sign, adapt, and extract, take a few milliseconds. The security of these protocols, we can, or at least we have analyzed it based on the properties of the underlying cryptographic schemes, the properties of after signatures. So we can do cryptographic proofs for them. Helps a little with the privacy in the sense that the application logic, or the application or the logic behind why the transactions are sent in this order and assigned in this order is hidden from the blockchain. The only thing that the blockchain sees is the transactions and the signatures, but the miners don't see how they were created and why, right? So the logic is on top. And finally, the only thing that we are putting into the blockchains are signatures, are a functionality that most of them support. So this approach also helps for interoperability. So if we go back to the landscape, so this is what this research direction is giving us. So we are having something that helps with atomicity. The example of atomic swaps, we can have two transactions atomically. It helps with interoperability because the only thing that we require is that the blockchain supports digital signatures. And for the privacy, it's a bit better, as I said, because we are hiding the logic. So how we create the transactions. But still, the blockchain sees the transactions. So you see who pays to whom and how many coins, for example. So it would be nicer if we can do something about it. So in the last 5 minutes, I'm going to tell you another direction that I'm also interested in, and is what is called off-chain protocol. So the idea is that, or the question that we were making back then was, okay, do we really need to put every single transaction in the blockchain? So do we really need to put all of them there? If we could even not put in them, it would be better for privacy because even the miners would not see that. The public ledger would not have this transaction. And what was back then was called payment channels. It's a fancy name for something that looks similar to what you have seen as the gift cards in some of the online shops. So in a gift card, you go to an online shop and you make a payment, like a bank transaction. and you load this gift card. And this is the bank or whatever payment system you use actually sees that. But now when you pay with your gift card, these payments are only between you and your shop. The bank or the payment system doesn't see that. So and you can do this as many times as you want. And at the end, when you are done with your gift card, you make a final transaction to redeem the funds that are there. So the bank only sees what is loaded here and what is sent back or refunded in the close, but the payments that you do in the middle with your gift card, this is not revealed to the payment system. So the idea of payment channels is similar. So we have a cryptographic protocol where we can create a funded channel in the blockchain. So this is seen in the ledger. But now we can make as many payments between two parties as we want, and this is not revealed to the ledger itself. And at the end, we will close it in the blockchain to redistribute the coins according to the payment that we have done. Okay, this is really high level. So I also, maybe let's see it with an example. So this is the ledger. So this is what is published in the blockchain. And imagine that Alice wants to open such a payment channel, such a gift card with Bob of 5 coins. So Alice will create a transaction where she logs 5 coins into a shared account. This is similar to what we have seen before, an account that is controlled by both, by Alice and Bob. And in order to get the coins out of here, you need the signatures from both, from Alice and from Bob itself. Now Alice signs this transaction and goes into the blockchain, everybody sees it, and now the coins are actually locked in this joint account. Now, from there, imagine that now Alice wants to pay 1 coin to Bob. Okay, so what Alice will do is create a second transaction where say, okay, out of the 5 coins that we have in the joint account, Bob, I want to redistribute it as I get 4 back and you get 1 for yourself. And Alice signs with this key and give it to Bob. And at this moment, this is a valid payment to Bob. This is a valid transaction. Why? Because the only thing that Bob needs to do extra is to sign with his own key. But because he actually owns that key, he can always do that and make a valid transaction. But instead, he would just not do it. He just keep it in memory and wait for more of these transactions from Alice. Imagine that now Alice wants to pay another coin, let's say 2. So Alice does a second transaction. We say, look, Bob, now we're going to distribute differently. So I'm going to give you 3. I'm going to get 3 back, sorry. And you're going to get 2. And I sign this transaction myself. And as the same argument as before, Bob is happy with this because the only thing left he has to do is to sign with his key, and he can always do that. And we can do this several times, as many times as we want, until Bob or Alice says, look, we're not going to use this channel. We are not going to use this gift card anymore. So I put the transaction in the blockchain, and they get actually their coins back to each other. So basically, the idea why this is interesting for privacy is that now we look at the ledger, what is actually published, what is really the miners, all of us can see, is that what has been opened, what was the initial balance of the gift card, what is the balance of Bob and Alice in the payment channel. But everything happening in the middle is only known between Alice and Bob. So the miners don't really see it. So that helps towards the privacy goal. And in general, this is the gist of this second research direction that is called off-chain cryptographic protocols. So the idea is, as before, create cryptographic protocols that help Alice and Bob to coordinate which transactions need to be done and how they have to be authorized. But instead of putting directly in the blockchain, they pay to each other in such a payment channel construction. That's the basic idea. And this is what is helping us for trying to target these three security, privacy, and interoperability properties. So in the last minute, a bit of shameless self-advertisement. So we have done many of these generic cryptographic protocols for blockchain applications, for different use cases, for payment channel networks, coin mixing, so several of them. From the more cryptographic scheme side, we have also, apart from the adapter signatures, we also did another scheme called verifiable witness encryption of threshold signatures. So it's another interesting building block that, for example, we are using it for building Oracle contracts. I'm really happy to talk about the details afterwards if you're interested. And apart from that, I wanted to share in the last slide all the other interests that I also have. So apart from looking at what is inside of the blockchain or the system, I'm also interested in looking at the system itself. I mean, at the end of the day, this is a system that is there. It's used by many users. There are many payments going on. So I'm really interested in looking at how the users interact with the blockchain itself. And so far, I'm looking at the security and privacy of them. And so far, we found, for example, a security attack on the Lightning Network, which is one system that users are using to pay to each other through payment channels, as we have seen before. And also, we developed an anonymous communication. There's a protocol is called CoinShuffle that is actually developed in wallets like Bitcoin. And the idea is that to hide who is the person sending the transaction to the miners. So we can hide when Bob sends a transaction to the miners don't know whether the sender was Bob, Alice, or Kai. And the second aspect from the system part that I'm interested in as well is that this data set is public. We have all this data there, and we can extract a lot of information from it. So I'm doing works where we are empirically looking at and analyzing this public data. For example, one thing that we did is that we developed this coin shuffle that is based on CoinJoin, and we analyzed how much people are using this protocol in the wild. So how many of these transactions happen using CoinJoin, and how much level of anonymity is given to the users on that. And also recently with the colleagues at IMDEA, we looked at how the current Bitcoin is used, for example, to get money for cybercrime, things like ransomware and so on. So how people are getting money from the victims using Bitcoin to receive the payment, the ransom payment, and how this money is distributed then in the system. And with that, I would like to finish. So thanks a lot for the attention, and I will be happy to answer any questions that you may have. Thanks.